Hi students, welcome to my lectures on chemical reaction engineering. Today we are going to discuss about one operation with temperature, which is the adiabatic reactor. Adiabatic reactor has many important roles in industries, and in today's lecture we are going to discuss on what conversion we can get if you know the temperature of the reactor. Okay, the whole agenda of today's point is, if you know the temperature of the reactor, which is an adiabatic reactor, then you can predict what is the conversion. If temperature is this much, the conversion from this reactor is this much. Okay, whether it is a batch reactor or CSTR or PFR, any reactor, if you know the temperature of the reactor, you can predict the conversion. So in today's lecture, we are going to discuss about this particular reactor, and to do that we have to go with a set of procedures. We need to do at least 3 to 4 steps are required. First of all, you should know the energy balance. You should know the terms in the energy balance. Next, you will get an equation in terms of enthalpy. Now you have to convert the enthalpy in terms of reactant A. Then there are next 2-3 steps are required to reach to the final one simple equation, but the derivation a bit long, so please be patient. This energy balance, what I am trying to teach, you can easily apply to other subjects like heat transfer, thermodynamics, mass transfer. You can apply the similar concept. I will make it as simple as possible. Let us go define. Our today's agenda is adiabatic reactor. What is the objective of lecture is find at temperature T what is the conversion X, whether it is a batch reactor or continuous stirred tank reactor or plug flow reactor. Only thing is you should know is what is the temperature T of the reactor. In case of batch reactor, what is the temperature inside the reactor. In case of CSTR means what is the exit temperature T, and what is inlet temperature is TR, nothing but reference temperature. Here what is the exit temperature of the products. If you know the inlet temperature is reference temperature, any temperature. Today's agenda is, if you know the T, you know the conversion in this reactor. If you know the T, what is the conversion in the plug flow reactor. All reactors are operated in a adiabatic way. That means, provide if you put an insulation around the reactor, no heat can go in to the reactor, no heat can come out of the reactor, no work, no shaft work is there in the reactor, no shaft work can be extracted, no shaft work can be done onto the reactor. So it is simple reactor. Let us do the general energy balance. From this general energy balance, let us go to the adiabatic conditions. Example, if you know this is any random reactor, it could be batch, it could be continuous reactor, any reactor. Let us take a section. Okay, there are some arrows which is showing inlet to the reactor, there are some arrows which is showing outlet to the reactor. You can see how many ways an energy can enter into the system. That is what, because we are doing the energy balance. From to the energy balance, you should know what are the different kinds of energies that are existing, so that how many energies can go into the reactor, how many energies can come out of the reactor. Okay, the arrows to the reactor indicating we are giving some energy, the arrow outside means we are extracting the energy from the reactor. Okay, this is what the basic plan. Okay, and what are the energies then enter into the reactor? You know, any molecule, because we have number of molecules in a reaction, so every molecule have some energy. What are the different kinds of energy a molecule can have? The energy the molecule can possess is represented by the term E, which is energy. The energy of a molecule can be internal energy, can be kinetic energy, can be potential energy, can be surface energy. Any energy a molecule can have. So that is why IE, internal energy, is represented by the symbol U. kinetic energy, potential energy, surface energy, and many other energies if it is existing. So, in our case, only internal energy is big compared to every other energy. So, that is why every other energy a molecule have is negligibly 0 compared to an internal energy. So, EI into Fi is nothing but how much internal energy a molecule is taking into the reactor. Fi into Ei means how much a molecule after the reaction, there are product molecules and unreacted molecules are there, how much energy they have. So, after the reaction some energy will come out of the system in terms of the product or unreacted molecules. So, that is Fi into Ei. Fi is the molar flow rate, Ei is the energy possessed by the molecule, okay, joule per mole. So, units of Fi is nothing but moles per second, unit of Ei is nothing but joule per mole of molecule. If you multiply these two, you get joules per second. Okay. How many joules per second is entering into the reactor? How many joules per second is exiting the reactor? Okay. What is the other arrows? This Fi into Wi. Okay. And here it is termed as flow work or PV work. That means if any molecule entering into the reactor, it has to push the things, okay, so that it can enter into the reactor. Okay. That is called the flow work, because the pressure and volumes are different in the reactor, the pressures and volume outside the reactor is different. When a molecule entering into the another chamber, that means from outside to inside, it has to do some work, otherwise it cannot enter into the reactor. So, that kind of work is called the flow work. So, Wi, that means Fi into Wi, how much molecule has to spend energy to enter into the reactor, and Fi into Wi is how much amount of energy a molecule to spend to exit from the reactor to the outside. That is called the flow work or PV work. So, that is why PV in, this is Wi out means PV out. And other way, if I am adding energy, heat energy, if I am burning, if I put some heat to the reactor, that means I am supplying some amount of energy to the system. That means this is called external energy, that is represented by Q. If the reactor is running some turbine or a shaft, anything from the reactor to the outside is negative. Okay, do not worry. This Ws is called the shaft work done by the reactor on the surroundings. The arrow is given the downward direction, means reactor is doing work on the surroundings. Okay. These are the inlet arrows. There are 3 inlet arrows, there are 3 outlet arrows. All inlet arrows are positive, that means giving some energy to the reactor. All these outlet arrows means they are spending some energy from the reactor to the surroundings. So, these 3 are negative, these 3 are positive. And that means if there is inlet energy in minus energy out is equal to energy accumulation. If some energy is getting accumulated in the reactor, that energy is called ESYS, system energy. Okay, this is the plot. Once you know the plot, okay, I have given what is Q, what is Ws, what are the units of EI, UI, Wi, Wi, what is joule per mole, Qs, joule per second, everything in the energy balance should be in terms of joule per second. That means I am counting the energy in terms of time. Every second how much energy is going into the system, every second how much energy is coming out of the system. So, to do that I have to multiply these sum terms like Fi into Wi, Fi into Wi is nothing but moles per second, because Wi has the units of joule per mole, Fi has the units of moles per second. If you multiply these two, finally you get the units of joule per second. That means whatever I do the balance here, every term should be in joules per second. So, this is the basis for our derivation to start with. Keep in mind what we are doing. Finally, we have one equation. That means in that equation, if you know the temperature, then the conversion you can able to get. That means from T, what is the conversion in the reactor? If 100 degrees centigrade is the exit temperature, then how much conversion is there in the reactor? So like that we are going to get one simple equation, but between that things are lengthy, so please be patient. So let us start the energy balance. Okay, energy in minus energy out plus heat added, shaft work subtracted is equal to energy accumulated in the system. This is called the basic energy balance. So what are the inlets? Inlet energies, one is flow energy in, second is molecule energy in. So that is why these two are plus. Out, flow energy out, molecule internal energy out. Okay, that is why these two are the outlets, plus heat energy added, which is Q, minus shaft work subtracted, which is minus Ws, which is equal to DES by dt, accumulation. So generally in industry, reactor operates in a steady state fashion. So at steady state, this term is 0. Now we have to deal with this term. You get every term sigma I equal to 1 to n term comes. What is, because in a reaction it is possible more than one molecule can enter into the reactor, more than one molecule comes out of the reactor. So all the molecules in, all the molecules out, we denoted by the symbol sigma. That is why sigma 1 to n inlet, sigma 1 to n flow inlet, sigma 1 to n this energy out, sigma 1 to n the flow energy out, plus Q that is added, minus shaft work that is extracted, which is called accumulated in the system. So a steady state it is equal to 0. Okay. Now simply substitute what is EI. EI is nothing but int EI is nothing but every energy is 0 except the internal energy. So in place of EI we have substituted UI. In place of WI flow work I substituted P into VI. Okay. Rest everything is the same. Now you know, if you common out Fi in these two terms, Ui plus PVy in, minus if you common out Fi here, Ui plus PVi out, plus Q minus Ws is equal to 0. If you remember, the enthalpy is nothing but internal energy plus PV work. Okay. Then U plus PV is nothing but Hi in, Ui plus PVi is equal to Hi out. Okay. Now this in and out, in representing inlet conditions. So here in our reactor the inlet conditions generally represented by subscript 0. Okay. That is why Fi, this in has become Fi0 into Hi0, this out has become Fi into Hi. So this is our first goal. We have reached, okay, one equation which comes from the energy balance. Now there is, because generally what happens, if any reaction happens, we generally take the basis per mole of A. If A is my limiting reactant example, per mole of A, how much is the energy that is getting produced. Here explicitly the reactant A is not there. So let us get that particular reactant A into this general equation. So let us take these two terms and we expand with one reaction and get the terms A reactant. Here if you see, now we are going to analyze these two terms. Let us see how I have done. A moles of A plus B moles of B gives rise to C moles of C plus D moles of D. If I divide the equation with A, 1 mole of A is giving B by A moles of B, reacted with B by A moles of B to form C by A moles of C and D by A moles of D. We have to do everything in terms of per 1 mole of A, that is why the stoichiometry coefficient of A should be 1, okay, because the basis for this energy balance is per mole of A. Okay. What is sigma? These terms I am going to evaluate, these two terms. What is sigma equal to Fi0 into Hi0? I have to expand. How many molecules are there in my system? 4 molecules, A, B, C, D. So, sigma, if I expand in terms of 4 plus inert, because in our reaction inert is also there along with the reactants and products. So, somehow we have to keep this inerts like nitrogen, air or any other argon gas, any other inerts is present in my reaction, we have to count that inerts also. So, let us expand. Fa0 inlet conditions, that is represented by the 0, Fa0 into HO0 plus Fb0 into Hb0, Fc into Hc0, Fd0 plus Hd0 plus inerts Fi0 into Hi0. What is F A0, B0, C0, D0? These are inlet flow rates of A, B, C, D and inerts. HA0, HB0 means inlet enthalpies, that means inlet heat content of A, B, C, D and inerts. Similarly, exit conditions, Fi into Hi, are 4 molecules plus inerts. Fa representing outlet flow rates, Ha is representing outlet enthalpies after the reaction. So, I know if you remember this from my stoichiometry lectures, Fa is equal to Fa0 into 1 minus x, Fb is equal to F0 into phi b minus b by a into x, like Fc, Fd, Fi. What is phi a, phi b, phi c, phi d, phi a is given. Now, simply substitute these in equation number 7 and evaluate the term this sigma minus this sigma. What I do is, I substitute all the terms in the equation number 7. Then I evaluate sigma I equal to 1 to n Fi0 minus Fi0 into Hi0 minus sigma I equal to 1 Fi into Hi, because finally I am going to substitute here. Okay. If you do that, if you common out few things, and because conversion, separate out the conversion term and the other terms, you get Fa0 into Ha0 minus Ha into phi a plus Hb0 minus Hb into phi b plus Hc0 minus Hc into phi c, this is in terms of phi d, plus Hi0 minus Hi into phi I inerts minus d by a into Hd plus c by a into Hc minus b by a into Hb minus Ha. If you see this is enthalpy of the products minus enthalpy of the reactants, nothing but enthalpy of the reaction. This term is called enthalpy of reaction into Fa0 into x. This is nothing but sigma I equal to, this particular term will become Fa0 into sigma I equal to 1 phi I Hi0 minus Hi. That means from here to here I kept it in only one sigma. This particular I have written as it is. Now you can see here only enthalpy terms are there, here in terms of Fa0 and conversion. Now our next agenda is, I know enthalpy, because finally my equation I have to relate temperature with conversion. Here you do not see any temperature term. Now our next agenda is replace this enthalpy terms with a temperature term. So let us do that. Okay, this term finally we got in terms of enthalpy. Now let us get the temperature term. I know heat content of any gas, heat content of any molecule, you have to start with this, it is standard state, because enthalpy is nothing but heat content. How much heat content, how do you know? Generally we have to start with their standards. If the standard is given in the solid phase and the reaction is in the gas phase, now you have to, your basis is, start with the reference enthalpy, go to the reaction enthalpy. Example, if a molecule is reacting in the gas phase, but it is reference is given in the solid phase, what happens? From the solid phase you have to take that enthalpy to the gas phase, then you have to put that value. So always in the thermodynamics, okay, you have to play with this standard enthalpies. For example, enthalpy. So you have to substitute the enthalpy of the gas, initial enthalpies of the gas, final enthalpies of the gas. So enthalpy of any gas, okay, if you know their standard state, you have to somehow calculate the enthalpy of the state. Example, a molecule, you have to calculate the enthalpy of a molecule in a gaseous state, but the standard is given at a solid phase. So, this is the enthalpies you have to consider. A summation of all these enthalpies is nothing but the enthalpy of the gas. Example, if the enthalpy of the same molecule is in the solid phase is given, that is your reference temperature example. Now, take that as a basis. Solid, you slowly heat up, it will become melt. Okay. Melt is nothing but liquid. From melting, you get slowly, if you heat, it will become boiling state. From the boiling state, it become a gaseous state. So, during this phase transformations, different enthalpies are existing. So, you have to summate all the enthalpies during its temperature changes to get the enthalpy of the gas. Example, if you know the enthalpy of the solid at reference temperature, now plus you heat the solid to its melting point. So, that enthalpy is nothing but enthalpy of the solid from reference temperature to melting point. Okay. At that melting point, what is going? Latent heat of melting. Okay. During melting process, some heat will be a requirement of heat will be there. So, that is the enthalpy of melting. From melting, that means it has become a liquid state. From the liquid state, it go to the vaporization state. That means liquid from Tm melting to the boiling temperature. At the boiling temperature, the liquid will become the gas or vapor. Then you have to enthalpy of vaporization you have to add. After vaporization, you need to heat, because now it become vaporization means it becomes a gas at a boiling point. From the boiling point, your reactor temperature is some other temperature which is higher than the boiling temperature. Then you need to add that particular enthalpy because at the reactor temperature. That means enthalpy of gas from boiling to the reactor temperature. Finally, if you add all these things, then you get the enthalpy of the gas at a temperature T. Suppose its solid is not given, liquid state is given as a reference. That means any gas enthalpy at any temperature T is nothing but, if a standard of liquid is given at TR, that means enthalpy of the liquid at TR. From the liquid, what happens? If you heat, it will become to the boiling state. Okay. That means enthalpy of the liquid from reference temperature to the boiling state. From the boiling state, enthalpy of the vapor or gas phase transformation happens. So, enthalpy of the vaporization at boiling temperature to my required temperature, which is T. That means enthalpy of the gas from boiling temperature to the working temperature, which is T. If you add all the things together, then you can able to find out the enthalpy of the gas at temperature T in my reactor. Suppose enthalpy of gas state is given directly. Here liquid state, you have to consider these steps. If the liquid reference temperature is given, then you have to add all these things to get the enthalpy of the gas. If directly standard state is the gas, for example, at reference temperature is given, that means if you want to calculate the enthalpy of gas at temperature T, you need given enthalpy of gas at reference temperature TR. From TR, you have to heat the gas from TR to T, because my working temperature is T. If you add these two terms, that is enough to get the enthalpy of the gas at temperature T. So, enthalpy of gas at reference temperature generally denoted by HI, standard temperature TR. That means enthalpy of gas at reference temperature is TR, plus enthalpy of gas from TR to T is nothing but integral TR to T Cp dt. If Cp is constant, it can come out of the integration and will become enthalpy of any molecule I at a given temperature. That means gas I am talking about, means enthalpy of I at reference temperature plus Cp into T minus Tr. That means you have to substitute in place of Hi0 minus Hi. Now the temperature terms will come. Okay. Let us see. Let us take this one term Hi0 minus Hi and see how the temperature will come. Hi0 minus Hi is nothing but, what is Hi0? Reference, that is Hi0 is talking about enthalpy of the gas inlet to the reactor. Enthalpy of gas inlet to the reactor is nothing but enthalpy of those gases at reference temperature plus reference temperature to initial temperature, because all the molecules enter the reactor at temperature Ti0. So, that is called the inlet temperature of all the gases. So, that is why Hi0 is nothing but Hi0 standard plus Tr to Ti0 Cp dt. Similarly, what is Hi? That means exit enthalpies. Exit enthalpy is nothing but its standard enthalpy, that is Hi0 at Tr, because everything in terms of reference temperature Tr only. So, this temperature plus Tr to T, because all the gases exiting the reactor at T temperature. So, that is why Tr to T, it is Tr to Ti0. Now, these two terms cancels out. Now, Hi0 minus Hi will become Ti0 to, because here I mean because you can see here, if I do this minus integral Ti0 to Tr Cp dt plus Tr to T Cp dt, here Ti0 to Tr and Tr to T will become Ti0 to T, because it starts with Ti0, ends with T. Okay. Ti0 to Tr plus Tr to T will become Ti0 to T. So, that is why Hi0 minus Hi is nothing but minus of Ti0 to T Cp dt. You know, Cp comes out, if it is Cp is generally constant, specific heat capacities within limited temperature range, it can come out of the integration. Now, it will become Cp into T minus Ti0. Okay. Now, you got what is Hi0 minus Hi is nothing but Cp into T minus Ti0. Substitute in this equation. Now, Q minus Ws minus Fa0 integral I equal to 1 to n phi I Cpi T minus Ti0 minus delta H of the reaction at temperature T into Fa0 into x. Okay. Now, here, okay, now I am done with this. Now, let us take what is the enthalpy of the reaction at temperature T. Okay, let us evaluate this parameter, because finally we have to take the temperature term on one side and react and conversion on the another side. What is delta H of the reaction, but what is the heat of reaction at reactor temperature? That is nothing but delta H of reaction at T is nothing but d by A into Hd plus C by A into Hc minus B by A into Hb minus Ha. That is enthalpy of the products minus enthalpy of the reactants. That is nothing but enthalpy of the reaction. Now, what is Hd, Hc, Hb, Ha? Similarly, the way we have done, we have to, that means what is Hd? Hd is nothing but standard reaction at standard heat of enthalpy of D at reference temperature Tr plus Cp of D into T minus Tr. What is Hc? Enthalpy of C at reference temperature plus Cpc into T minus Tr. Like that, evaluate all the terms. Now, if you take standard enthalpies on one side, temperature enthalpies on the another side, you can see d by A into standard enthalpy of D plus C by A into standard enthalpy of C minus B by A into standard enthalpy of B minus standard enthalpy of it has become, everything is in the standard state. That is why this particular term in this bracket is nothing but standard heat of reaction at temperature Tr. Sorry, this is Tr actually. This is standard heat of temperature at Tr. Del Cp, you can see Cp of D plus Cp of C minus Cp of B minus Cp of A. Okay. This is nothing but specific heats of products minus specific heats of the reactants is nothing but del Cp, okay, differential Cp into T minus Tr. This is our final equation. Here Tr, it is not T. Okay. This is what delta H of the reaction, that means enthalpy of the reaction at temperature T is equal to enthalpy of the reaction at standard temperature Tr plus del Cp into T minus Tr. Let us substitute equation number 13 in equation number 10, 12, I mean you can see 13 and 12, this is the 12, and the final equation has become, let me check, This is the Q minus Ws into Fs0 into I equal to 1 to n phi I Cpi into T minus Ti0 minus enthalpy of reaction. Imagine if all molecules are entering at same temperature, which is T0, okay, then Ti0 become T0. If you substitute, if you rearrange this equation, x on one side, everything on the another side, that means there you get for adiabatic conditions, conversion is nothing but sigma phi I Cpi T minus T0 divided by minus of delta H standard reaction plus del Cp into T minus Tr. That means if you know the terms on the right hand side, you can know conversion from the left hand side. XEB is given. What is X? Conversion, because this conversion has coming from the energy balance. So, XEB I have denoted in the Fogler book, you can follow, I mean conversion from the energy balance, XEB. That means if you know the temperature, you can know the conversion in the reactor. This is the final equation we can able to say, see all the things we have done till now to reach to this point. If I given my reactor temperature, what is my conversion? And this is the linear equation. See, if I plot conversion and time at temperature for exothermic reactions, okay, and just a second, a small correction is required. Yes, if you see the graph, okay, the graph talks about the conversion on y axis, temperature is on x axis. From this equation, we can say that if you increase the temperature, the conversion will reduce. If you, if the same equation, if it is an exothermic reaction, endothermic reaction, that means this is endothermic. For endothermic reaction, if you increase the reactor temperature, the conversion will increase, because for exothermic reaction this term is negative, for endothermic reaction this term is positive. So, accordingly you get this kind of plots, because this is a linear equation. Always if you increase the temperature, the conversion will decrease in exothermic reaction. If you increase the temperature, the conversion will increase for endothermic reaction. That means from this equation, if we know the reactor temperature, we can predict what is the conversion in a adiabatic reactor. Okay. And with this equation, let us solve one example to get the conversion value. Let us do that.